can't help them much. Okay.
Hi, I'm Momin. My project partners are Wenting and Shayak, and we are extending fair classification techniques to non-binary features. To explain the background problem is when we learn on a lot of data, there's already inequalities entrenched in the data. And we can hide things like gender, age, or race, or whatever. But as we can see from this table here, that data about that inequality is already in the data set. So here we can see that on average, a higher fraction of whites have income above 50,000 as compared to blacks or other races. So just hiding race would not be enough to sort of correct for the discrimination that's in here. We implement this idea by Zemel et al. To completely hide all the protected features by this sort of weird approach, but it works pretty well, of designing prototypes. Every observation, you map it to a projection into this set of prototypes. Each prototype has a certain projection itself into features, and that hides the data. And the one thing about this, and I'll explain more about the model in a second, is that it only applies to a binary protected feature. And what we said is that, well, there are a lot of things that we would like to protect that aren't just binary, and that there is a kind of natural extension to multiple binary features, which would be the same as a multi-class protected feature, or thresholding or quantiles for a continuous protected feature. So this is the general overview of the model we're using, and specifically our extension to it. So you have your observations, you have the labels, and you have a certain number of protected classes that membership in that is binary. Either it's a member or it's not. We pre-specify a number of prototypes to learn. This is sort of like pre-specifying the K and K-means or something. We have the probability of mapping an observation to a prototype, and then we sum over all examples in a protected class, and that gives the probability of the member of class J is mapped to prototype K. We want to equalize this probability of being mapped over protected and non-protected classes. More specifically, we parameterize the probability of mapping a prototype as sort of an exponential of a distance function, appropriately normalized. And the sum of all observations in that class is then the probability of any member of the class. And what we want to minimize is the probability of a particular class being mapped to prototype K versus a member of a non-protected class being mapped into prototype K. We got in touch with the authors of it. They told us how they did it. We sort of managed to reconstruct that with a lot of difficulty. Theano, as you can see from this, it's over a class, so a single observation isn't really any good. Full batch is too expensive, so we use mini-batch stochastic gradient descent. This is only to map to prototypes. Once we do this optimization for creating prototypes, then we apply a classifier on it, we use regularized logistic regression, 2 implementations, same results. We use this on benchmark data sets from the CI repositories, same as the original paper did on the adult and German data sets. Adult is much larger, and that was sort of the more interesting data set. Error results. The first set of bars is the binary feature. So that's the original implementation. The second is a categorical, and the third is continuous. So as you can see, the accuracy drops slightly for all types of features, but not by that much. When we compare their discrimination score, which is defined here, for the binary feature, it drops a lot. For the other, there is a drop in discrimination, but it's not as dramatic. So the extension doesn't work as well for multi-class features. Also, the idea being that the protected feature should be completely scrubbed from the data once you're using these prototypes. It works very well for the binary, very poorly for the multi-class, and sort of okay for the continuous. And we have different measures of ability to predict. The binary is accuracy, the continuous is R squared, and I don't remember what the softmax was. So in conclusion, we existed in implementing approach. We extended it to a multi-class. We saw how well it works. It doesn't work as well for multi-class and continuous, but it still works kind of well. We're currently working on another completely different approach to fairness in classification, which uses a regularizer in order to achieve fairness. And that we're, again, still working on and tuning to implement, and we'll ultimately compare how well that entire framework works versus this entire framework. Thank you.